Okay, guys, let's do some gas laws. So I have for you here, I wrote down all the gas laws. I'm going to scan this and have it in the PDF so you can look at it. But these are all the different gas laws we learned. And no, I will not give them to you on the test. You have to know your gas laws. You have to memorize them. I know it's annoying, but that's how it is. You also need to know what R is. Actually, I give you R on the test? I'll look and let you know for sure. But it's 0.0821 atmospheres times liters over moles times Kelvin. How many liters are in 1 mole of gas at STP? That's the 22.4 that we added to our mole conversions. What's STP? Standard temperature and pressure, which is 1 atmosphere in 0 degrees Celsius. Okay, so this is just kind of background knowledge to know. And now let's do some math. So first of all, if you have a gas occupying 83 liters, 766 millimeters mercury, what's the pressure at 25 liters? So we have a volume and a pressure, a new volume, and we're looking for a new pressure. So that's going to be Boyle's law. With Boyle's law, we just have to make sure the units are the same and both of the volumes are in liters. Our answer will be in millimeters of mercury because that's what we have. So I can go 83 times 766 equals X times 2.5. And then I'm just going to throw this in my calculator. Boop-a-doop-a-doo. 83 times 766 divided by 2.5. And I got blah, blah, blah. I got a really big number. Okay. I'm going to have to round that to 2 sig figs because that's what I have. So it's going to be 25,000 millimeters of mercury. All right. The next one, gas has a volume and a pressure and a temperature. What would be the temperature at a new volume pressure? So here we have volume, temperature, pressure. So we're going to be using the combined gas law. We want to make sure our units are the same. Volume is both in liters. Pressure is both in kPa, but we do need to change our temperature to Kelvin. So I'm going to take my 23.4 plus 273.15, but round to 1 decimal place because that's what I have here. So I'm going to do 296.6 Kelvin. And then I'm going to put this into the combined gas law. So I'm going to say 56.3 times 98.6 over 23.4. No, it's not 23.4. It's 296.6 because it needs to be in Kelvin. And then 10 times 253 over x. And then just mathing it to solve for x. Mathing it. It's a verb now. And that's how all the cool kids say it. So if you want to be cool like me, that's how you're going to say it. I know this is really exciting watching me put things in the calculator. I am putting it all in at once, but what I'm dividing by, I'm putting in parentheses. And I get out x equals 135 Kelvin. I'm just checking my sig figs. Yeah, 3 sig figs is my lowest. Okay, so a gas at STP has that many volume. What is the pressure of the gas at this? Okay, so this is another combined gas law because we have a pressure, temperature, and volume, and we're finding a pressure with a new volume and temperature. So again, I'm going to have to change my temperature to Kelvin. So 6.52 plus 273.15. So that's going to be 279.67. STP is 1 atmosphere, 0 degrees Celsius, which is 273.15 Kelvin. My volumes, one volume's in milliliters, the other's in liters. I'm going to change this to liters. It really doesn't matter. You could have changed this to milliliters and it would be the same thing. Now that I have all my appropriate units, I can plug it into the combined gas law. So I have 1 times 0.987 divided by 273.15 equals 1.32 times X over 279.67. And then again, I'm just throwing this in my calculator because when I have problems like this, I think of it as plug and chug. You plug in the numbers into the formula and then you chug out the answers by doing the math. And I got here X as 0.7. I'm just looking at my sig figs. I think I have 3.766 atmospheres. Okay, so that's how I would do this first page. Now let's go on to the second page. So, first of all, here we're converting some pressure units. You do need to know, you should know ATM, kPa and torr / millimeters of mercury. PSI, I don't think there's any on the test. Again, I can look at that, but PSI, it's 14.7. Torr in millimeters of mercury is 760. kPa is 101.3, and ATM is 1. So here for the first one, 26.9 PSI. I'm going to divide it by 14.7 PSI times by 760 torr. Again, I'm just throwing this in my calculator. And rounding to the same number sig figs I started with, which was 3. So I get 1390 torr. On the next one, I'm going to do my 225 kPa, divide by 101.3 kPa times by 1 atmosphere. And I get out 2.22 atmospheres. The next one, 120 millimeters of mercury. So I'm going to have down here 760 millimeters of mercury to 101.3 kPa. And it goes to 136 kPa. Okay. Pressure conversions, it's doing the dimensional analysis like we have always done, but we just need to know our conversion factors. Okay, next, how many grams of carbon monoxide are in 783 liters at STP? Okay, so here we're not changing anything, so this is PV equals nRT. So our pressure is 1 atmosphere because it's at STP. Our volume is 78.3 liters. N is what we're going to be looking for. We're looking for grams, but moles will get us to grams. R is always 0.0821, and our temperature is 0 degrees Celsius or 273 Kelvin. Plug this into PV equals nRT, so 1 times 78.3 equals X times 0.0821 times 273, and X equals, let's do the math, divide by 0.0821 times 273, and I get out 3.49 moles of carbon monoxide, CO, but I want grams. So now I'm going to use my molar mass. So I'm going to take the mass of carbon plus the mass of oxygen to convert it to grams. And I end up getting 97.8 grams of carbon monoxide. Oh, can you see that? There you go. All right, the next one, what's the pressure when we have grams, volume, temperature? This is another PV equals nRT. So PV equals nRT, we're looking for the pressure. The volume is 5.64 liters. N we don't have, but we have 14.5 grams of chlorine gas. Chlorine's a diatomic, so it's going to be Cl2. PVNR is always 0.0821. Temperature here is 32.8 degrees Celsius. So I have to do 2 conversions before I can do PV equals nRT. I'm going to convert my grams of chlorine to moles. If I was a better teacher, I would be writing this all out for you, but I'm not. I'm just putting it in my calculator, mostly because there's not a ton of space on this paper. So I got 0.205 moles of chlorine gas. And 306.0 Kelvin. All right, so now I'm going to plug this into the formula. PV equals nRT. I did not get a play for you because we weren't in class. My song about the ideal gas law that goes PV equals nRT. The gas laws are good to know. You use them everywhere you go. We're talking heavy duty chemistry. We're talking PV equals nRT. Aren't you super sad you missed that song? I'm sure I could find it on the interwebs somewhere, but I didn't. All right, so I got for my pressure 0.913 atmospheres just by doing the math. Okay, on the next ones, we have a balanced chemical equation, woo, which basically tells us we're doing stoichiometry, woo, woo. So here, how many liters of carbon dioxide can be produced from 26.7 grams of baking soda? So I need to get my grams of baking soda to moles of carbon dioxide. All right, so I'm going to take the baking soda is the NaHCO3. I'm going to need the molar mass of baking soda. So let me put it in my calculator. I'm getting the numbers off the periodic table. Honestly, I'm not because I have them memorized, but that's how you would do it. And I get the molar mass as 84.01. And then it's a 1-to-1 mole ratio to get from sodium bicarbonate to CO2. So this is how I'm going to get my moles, or the N for the formula. And I get out 0.318 moles of CO2 gas. So now I can do PV equals nRT. I'm STP. So I'm looking for the liters. So I have my pressure. It's 1 atmosphere. I'm looking for my liters. N is what I just found. R is always 0.0821. And temperature was 0 degrees Celsius, which is 273 Kelvin. So I'm going to put this all in my calculator. And I get out 7.13 liters. Cool. Oh, I could have done that way easier. Oh my goodness, you guys should be yelling at me. Because it was an STP, I could have just times this by the 22.4. Let's see if I get the same answer when I do that. 267 divided by 84.01 times 1 divided by 1 times 22.4. Oh, look, I got 71.12 way faster by remembering that 22 liters equals 1 mole when you're at STP. I did this the hard way. Gets the same answer, just it's the long way. On 21, however, you cannot use that because it's not STP, so you have to do the long way. So it's basically the same type of question. It's actually the same amount. We just have a different temperature and pressure. All right, so let's do some converting. I already have moles of CO2 because I did that up there. I'm not going to do that again. So this is going to be 0.318 moles. Let me get my temperature in Kelvin. That's going to be 348.5 Kelvin. And let me get my pressure in ATM. And that's going to be 1.12 ATM. So I have my pressure, my looking for my volume equals 0.318 times 0.0821 times 348.5 Kelvin. Okay, let's do this again, but now we're actually supposed to do it this way. On that first one, I was supposed to realize I didn't have to do all the work, but I didn't. So, sorry. and I got out 8.12 liters for this one. All right, and then we have our Dalton's law of partial pressure. Oh my goodness. Okay, so let's do this one. It was just on the homework we just did. I remember it. I have the homework right here. Maybe I'll look. No, I won't cheat. Okay, so we have 3 grams of O, N, and HE. We want to find the partial pressure and the total pressure. So we're going to be doing PV equals nRT 3 times to get their pressures. We have our temperature, we have our volume, we have grams. So what we need to do is convert the grams to moles for each of these. So 3 grams of O2 is going to go to divide by 32.00. 3 grams of N2 is 28.02. And 3 grams of hydrogen is 4.00, I believe. Okay, so let's convert these. 3 divided by 32 is going to be, I have 0.094. 3 divided by 28 is 0.11. It's 0.107. We'll round to 0.01 because we have 2 sig figs. 3 divided by 4 is going to be 0.75. I'm going to do PV equals nRT over all of these. I have a nice graphing calculator that I don't have to type everything each time, which is nice. And I'm just using the PV equals nRT formula because I can. So I got, for the pressure of oxygen, 1.7 atm. Now let's do it for the nitrogen. I get, it's 1.95, so it's going to round to 2.0 atmospheres. Pressure of helium is 13 atmospheres, so I'm going to add those all up. Remember, with adding, you round to the least number of decimal places, which is the pressure of the helium. So I had 16.7, so I'm going to say the total pressure is 17 atmospheres. Okay, so that's how you're going to do that one. And then on 23, this is a Graham's law of partial pressure problem. So an unknown gas effuses 1.66 times as rapidly as CO2. What's the molar mass of the unknown gas? So the unknown gas is 1.66 times more than CO2. So that's, CO2 is 1 because that's times more. I could have picked any number for CO2 and then just times it by that, but 1 is the easiest. Okay, and then we have to reverse it. So since this is CO2, I'm going to put the molar mass of CO2 up here. And yes, I just had that in my brain. And then we're looking for the molar mass of the unknown. So first thing I have to do is square both sides. So I'm going to take 1.66 squared. And I get 2.76 equals 44.01 over x. I'm going to multiply both sides by x. And then I'm going to take 44.01 divided by 2.76. And I get a molar mass of 15.9 grams per mole. What could that be? That could be a hydrogen bonded to nitrogen, but that's weird. 2 nitrogen. I don't know. I could probably spend more time and figure out what that's supposed to be, but I don't want to. All right. So, yeah, that is how you do Graham's law of partial pressure. So again, I'm going to post the PDF of this so you can look at the work more closely. But if you have any questions, let me know. Study, study, study. Be ready for Module 10 test.